explicit formula. Let me remind this formula right now for this DH. Do you remember, right? You remember this DH GM. And we will use this explicit formula in order to prove the loop equations. So what do we need for topological recursion? We need to prove the linear and quadratic loop equations, and we need to prove the projection property, right? We have proved that this is equivalent to the original definition of topological recursion. Please feel free to interrupt me if there are any questions. So we will, today we will start with this formula with which we have ended up with last time, and we will prove the loop equations. Regarding the projection property, I will briefly describe the logic, how to prove them, but we won't have time to do this explicitly in all detail. So let's recall this formula. For brevity, I will use the notation W, so I will denote by WGN this D1 and so on, DN, HGN. Do I have to recall what is this capital H? How it is obtained from the from our partition function from Z? You remember, right? So that H is, in this case, it's connected function, right? And it is obtained by taking derivatives of logarithm of this kp tau function and then putting all the remaining p variables to 0, right? And the disconnected variant with the bold black circle is the same, but you take the tau function itself and not its logarithm. I will not write it down because we have done it multiple times. Now, what do we have for this W? So we, in fact, this holds for n greater than 1. So for n greater or equal than 2, and Gn not equal to 0, 2, we prove that Wgn is equal to the coefficient in front of h 2g minus 2 plus n of un and so on u1 applied to the sum over all connected graphs, connected simple graphs of this product over all edges of WKL. Here we have the product over all edges in the connected simple graph. So you remember this formula, right? And we, by the way, is the recording enabled?
Yes. Yeah.
Okay. So let's recall who are these guys. So WKL is just this expo h squared UK UL S of UK H ZK DZK S of UL H ZL DZL Y to ZK ZL over K minus ZL squared and minus 1. The whole exponential is taken. And then for U, sorry, ui applied to f is this sum over j and r from 0 to infinity, but we remember that this sum, once you consider a particular power of each bar, in fact, this sum is finite. So you can extend it to something like 2g or something like that. Maybe 3g is enough. I don't remember precisely, but we discussed it last time, that in fact, instead of infinity, you can safely write something like 3g here, and even less probably. So this is a finite sum, in fact, di to the power j applied to the coefficient in front of vj, v to the power j of lr v, which also depends on v and y and h bar, divided by qi, coefficient in front of u I to the power r, x of ui s of ui h bar, sorry, I'll write z over dz that way. Zi applied to minus 1 applied to y, and then h s of h here f. And then let me recall what is Q and L. So L is LR is dy plus v side run of y. Okay. To the power r x of v s of vh bar dy over s of h dy minus 1 applied to side y. And that's it. And Q is just z over x dx over dz, which is equal to 1 minus z y prime of z psi prime of y of z. So we recall that x is z over x of psi of y of z. So you remember all of this, right? We start with this formula, and we want to prove, starting with this formula, we want to prove the loop equations. Okay? Now before doing this, let me reformulate the loop equations a little bit. So, reformulation of loop equations. How will I want to reformulate it? Let me introduce what's called I'll call this space. So I have my sigma. Okay, sigma was the Riemann surface. Now our spectral curve, if you remember, is sigma x y, where in this case x is log capital X. So this is our spectral curve, and if you remember the loop equations, they stated that we formulated them in terms of omega, right? But they can be reformulated in terms of W, right? So first, in terms of W, first version is that linear loop equation is in terms of W, saying that so here let's say that dx equals 0 is the same as Zn P1 and so on Pn. So we have capital M critical points x, which is critical points of small x and capital X are the same, and we call them P1 and so on Pn. Okay. So we're saying that linear loop equations are satisfied when for all G and M, for all I from 1 to n, W Gn of Z, let me write it, Wgn plus 1. Wgn of Z, Zn plus Wgn plus 1 of sigma I of Z, Zn is homomorphic. Okay, so for at all critical points, this combination is homomorphic. If you remember, when we formulated this in terms of omega, we said that omega should be homomorphic and also have a 0 of at least first order, right? But for W, it's equivalent to saying that they're just homomorphic, because how are W's related to omegas? Let me recall this, maybe over here. So recall that W, want to write it the other way around. So omega Gn is Wgn times product dxi over xi, I from 1 to n, which is the same as saying that they're equal to Wgn times the product of d small x, right? So this is how omega is related to W. It's easy to figure this out, because if you remember, omegas, they were okay, so we need to recall that they are d1 and so on dn, just taking ordinary differentials of hgn, and wgn is d capital 1 and so on d capital M hgn. So combining this and this, you immediately arrive at this statement. Is it clear why omega is related to W precisely by this factor? It follows from this and this. where capital D is where di is xi dx derivative with respect to capital
dxi means d partial derivative due to xi, so d over dxi.
D over dxi, yes. So I think this is clear, and it's now clear that if you look here, if we look at some point pi, then obviously dxi, because pi is the critical point, dxi has a simple zero there, because we said that all those critical points are simple. Meaning that if W is just holomorphic, then omega will be holomorphic and have at least a simple zero. Right? Do you agree? Look here. So let's look at the point pi and say that W is holomorphic there. Then W is multiplied with dxi. dxi has a simple zero at pi because pi is a simple critical point of dx, of x, right? Then omega will not only be holomorphic there, but also have a zero of at least order 1. That's what I want to say. So that's why we can formulate the linear loop equation like this in terms of W. Okay?
Там голоморфность нужна и 0 порядка, хотя бы 1.
Для логики. А для W просто голоморфность.
То есть да, мы когда там когда-то несколько месяцев назад проверяли линейные и квадратичные петлевые уравнения, мы проверяли голоморфность плюс для омег, но голоморфность плюс наличие нулей. А вот тут, если в терминах дубль v больших, то это просто голоморфность.
Голоморфность, потому что наличие нуля, оно появляется, когда вы приходите на W.
Домножаем на dx, у которого 0 там по определению.
Все понятно? Okay, and now the same regarding the QLE, the quadratic loop equations. Same thing is that for all g n greater than 0, for all I, w g minus 1 plus 2 of z sigma I of z Zn plus sum g1 plus g2 equals to g, and I and j give the whole set n, wg1 of z zi times wg2 j plus 1 of sigma I of z zj. So this is again holomorphic. Same thing as with the linear loop equation. When we describe this in terms of omega, we required that this guy should not only be holomorphic, but it should have a zero of at least degree 2, right? Order 2. And here we just say that it's holomorphic because it's multiplied by dx 2 times. And we get a zero of order 2. Okay, but this is not where I want to stop because I want to reformulate it even more, this condition, because from here it's not very easy to see that these conditions are satisfied by my formulas above. So I want to to reformulate it in yet another form. I'll put 2 here. Second reformulation will involve the so-called space psi. So I'll denote by this capital psi the space. It's the space of functions. The space of...
This is the letter Xi capital, if you... It's not very common, but yeah, it's a Xi capital.
Yeah. This is Xi capital. So this is the space of functions on sigma, such that in the vicinity for all I.
So, do you want to define it as generates by x dx?
Yeah, I wanted to do this. That for all I, they in the vicinity of pi, space of functions f. No, sorry. They belong to the span of the following things, namely x d or dx to some power j applied to f of z, where f is a regular near pi. So what does it mean? What does it mean? What does it mean? This means that this will be the first problem for the seminar, problem 1. Equivalently, psi is the space of all functions with odd principal part at pi in local coordinate nu I such that nu I squared is x of x minus x of pi. So remember that pi, again, it was a critical point, a simple critical point, meaning that there is some local coordinate that small x looks like nu squared minus plus a constant, right? At this point, near the point pi. And the claim is that the space, which we're considering here, this space psi, is precisely the space of functions whose Laurent series at points pi have odd principal part in this local coordinate. So all negative powers, if you consider Laurent series of these functions belonging to the space psi, their negative parts of their Laurent series taken in the local coordinate, this local coordinate, have only odd terms, odd powers. Okay? Is it clear, the statement?
Я не понимаю, откуда может взяться там главная часть, когда мы такие операторы применяем.
А смотрите, на самом деле вот эта вот штука x d под x, если вы его перепишете в термины такой локальной координаты, то можно увидеть, что он будет устроен как единица на ню d под ню. И единица на ню d под ню, примененная к голоморфной функции, например, просто ню.
Ну, к многочлену какому-нибудь от ню, да.
Конечно, но не касается к ню. Вот что даст единица на ню d под ню, примененная к ню?
Вот у нее.
Один делить на ню. Она вам даст нечетную часть первого порядка. А если вы еще раз примените единицу на ню d под ню, она вам даст опять нечетную единицу на ню в кубе. И так далее. Вот это мы на семинаре разберем. Ну, утверждение понятно, да? So the claim is that precisely this space psi is the space of functions, meromorphic functions, let's say, meromorphic functions. Meromorphic functions whose Laurent series at pi are precisely have the odd principal part.
То есть это все такие мероморфные функции, которые в точках pi имеют нечетную главную часть.
Ну, то есть, вот если смотреть именно в локальной координате ню,
да.
Такой, что x представляется как ню квадрат плюс константа, вот это именно та самая локальная координата, которая естественная в критической точке такой, то в этой локальной координате ряд Лорана он должен иметь только нечетных степеней отрицательные члены. А почему нам это интересно? А потому что утверждение, что первое утверждение. И это, наверное, тоже мы на семинар оставим. Значит, проблема вторая задача. So problem 2 is W satisfy the LLE, the linear loop equation, whenever WGN belongs to psi. No, well, I want to, let me say that for all G and N greater or equal than 0, W of WGN of Zn belongs to psi of Z. By saying psi of Z, I'm saying that I consider only the first argument. But this, remember that all W's and all homologies are mathematically symmetric. Then it is enough to make the statement regarding just one of the arguments. Because psi of Z means that I consider this, I fix all the other Z1 and so on Zn, and consider this as a function in single variable Z. And it should belong to this space psi.
Это более-менее очевидно.
Это более-менее очевидно, на самом деле, действительно, потому что помните, что кто такое линейное петлевое уравнение? Это вам нужно взять там W и прибавить W от сигма от Z. Но как устроена локальная координате ню сигма от Z? Сигма от ню это минус ню, потому что ню так было выбрано специально. Но мы это на семинаре обсудим немножко подробнее. Вот. И поэтому и условие на то, что главная часть нечетная, автоматически будет следовать, что выражение, которое в петлевом уравнении стоит, оно как раз голоморфно, потому что все главные части сократятся, если там только нечетность. We'll see on the seminar that this holds. And problem three, which is a little bit more complicated, it says that, in fact, quadratical equations can be formulated in terms of this space xi. Again, the same thing, W's satisfy QLE. Again, whenever, so here I need another definition. So I want to, if you remember in this quadratical equation, let us go a little bit back, we had some expression involving W where you plug Z and sigma of Z, okay? But what if we put here instead of sigma Z of Z, what if we put, again, just Z? Let me write it down. So I will first introduce some definition. I will call it curly W2. The curly W2 GM is W, by definition, it's W G minus 1 and plus 1 of Z G n plus 1, let's say. Z Zn plus sum over G1, oh, sorry, G minus 1 and n plus 2 of Zn plus sum over G1 plus G2 equal G J equals N W G1 plus 1 of times W G2 G plus 1 of Z. Okay, it is the same expression as in the quadratical equation, just that instead of sigma of Z, I just have Z everywhere. Z, 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 Z. Okay? Is it clear what is the difference? So, and then the claim is that W satisfy QLE whenever for all G and N greater than 0, for all I, for all G and N greater than 0, curly W2 G n plus 1 belongs to the space This is a little bit more complicated to see than the linear loop equation, but not very complicated, so we'll do this on the center. Is the claim clear? Понятное утверждение. Утверждение, что когда мы здесь вместо одного из z подставим сигма и получится что-то голоморфное, это то же самое, что когда мы это не ставим не сигма, а просто z, что такая штука должна лежать в пространстве в этом кси. То есть иметь только нечетную главную часть.
Да, то есть как бы общий смысл того, что сейчас Петр Игоревич сказал, и то, что произошло, что раньше были такие петлевые уравнения для омег маленьких, которые звучали как омега от z плюс омега там, от сигма от z, голоморфно, плюс имеет 0, например, первого порядка, если это линейное петлевое уравнение. А теперь вот это сначала переписали на языке W прямых, а потом на языке вот этого пространства кси, которое пространство мироморфных функций, у которых нечетная главная часть в этих точках полюса, в этих точках P и T. И потом еще вот ввели это определение кривые W, которые просто для удобства на самом деле. Вот, киньте.
Сейчас, но если у нас есть эти линейные loop equation, то тогда это кривая W, но она там...
Здесь предполагается, что assume that LLE are satisfied.
Да.
So for this problem 3, this holds only if we already have linear equation. Ну, разберемся с этим, если аккуратно. Okay, so now I want to prove the linear loop equations for our case. Let's go back to our W formulas for all W's. We have explicit formulas. I'll maybe even make the zoom level a little bit less. So I go back to the first. To the statement which we obtained last time, to the explicit formula. Let me maybe highlight it by yellow. And we want to see from this huge complicated formula that in fact these WGNs, they all belong to the space C side, this capital side, right? But in fact it's quite easy to see. What do we need to see this, right? Let's look at our formula and look where can the poles at the points Pi come from. Where can these poles come from? Obviously, they come from Di, right? Because it's Di is x d over dx, capital X, or d over d small x. So obviously, each d it adds one order of the pole at the point Pi. Okay, do you see this? Where else can come this? Where else can come these poles from? They can also come from Q, right? So Q, because Q is Z over X. So we're looking at this formula, and we're trying to figure out where can the poles at Pi come from. So consider fixed sum I, and let's look at the point Pi. And where can poles at this points Pi come from? I'm saying that they obviously can come from Di, because Di is, let me write it somewhere here. Di is xi d over dxi. So obviously, or is the same as d over
This I in P and I in D are not the same, so it's just a coincidence.
Maybe let's.
Yeah. Well, in point K. Oh no, we will also have K here.
PM.
Yeah.
So let's study the behavior at PM. To fix some M, and let's look at the behavior of this guy at PM. Where can the poles at PM come from? It's clear that they can come from Di, right? Now, we're interested only in the dependence on Z1, let's say. So let's look at only U1. So this will be D1 to the power J, right? So behavior at
But
Z1 tends to PM.
but wait, if dx is 0 in P, so d1 creates a pole.
So D1 is equal to D over dx1, right? But x1 has a critical point at PM. PM is one of the critical points of x1, right? of the function x1, which means that this guy has a pole. It produces a pole. It applies to some function, right?
Я вообще не понимаю. Голова. Иксы это ж не локальные координаты.
Иксы это не локальные координаты.
Как мы по ним дифференцируем?
А в чем проблема?
Ну, у нас есть замена перемен на x большое от z маленького.
Есть формула, что вы всегда можете сказать, что d от d...
А, вот она тут написана.
От z это есть то же самое, что d от dz, ну, а здесь надо умножить на dx, сейчас.
Ну, на производную вот этой дроби z делить на e в степени 50y от z по z.
От z итера, d от z итера, dx от z итера, вот от z итера. Вот минус r.
Ну ладно, хорошо.
Все, в порядке. Вот по этой форме можно решить. Ну и легко видеть, что как раз если какая-то точка PM это критическая для x, то вот эта вот штука будет иметь пользу. Да? So we clearly see that D1 produces poles. Q1 can also contribute to the pole, right? Because Q1 is z over x, dx over dz. Again, it has a pole that is zeros. 1 over Q1 has a pole that is zeros of x of dx1, right? Where else can the poles come from? Nowhere else. Everything else is regular. Because we assume that y is regular there in the definition of topological recursion. The y is regular at this point, and what else? I mean, nowhere else can a pole come from. So it's basically our we can clearly see from this formula that WGN is a sum of expressions of the form d1 to some power j applied to q1 to the power minus 1, where fj is regular, where fj is regular, at z1 tending to Pm. Okay? This is clear from our formula. But what can I say about functions like this? First of all, can we see that if f is some regular function, does f of z1 divided by q of z1, does it belong to cathodic side? Obviously it does, because q, again, it has a simple zero at Pm. It has a simple zero. So this is some Laurent series with at most simple poles. So it's odd. It doesn't have any poles of order greater than 1. Any terms in the principal part of the Laurent series at any of the points of these points pi with order greater than 1, right? No negative powers of order greater than 1, because q by definition is z over x dx over dz, and dx has a simple zero at pi. because it's simple zero, then this has at most simple poles. And it automatically belongs to psi. If something has only a simple pole, its principal part is always positive. And then we apply to it some powers of d, but using the other definition of the space psi. Remember that space psi was spanned by applying some number of d's to regular functions. Then obviously d preserved psi. So d psi is a subset of psi. So the operator d, it preserves the space psi. So then obviously this guy is again a function in psi. So the linear loop equation automatically holds.
То есть это может быть, на первый взгляд, немножко контринтуитивно, потому что мы вроде говорили про голоморфность каких-то выражений, а теперь говорим, что там мы разрешаем полюса и так далее, но вот утверждается, что это действительно равносильные определения.
Ну, мы это обсудим на семинаре, там легко видеть, что условия голоморфности того, что когда вы берете W от Z плюс W от сигма от Z, это то же самое, что вот функция лежит в пространстве xi, то есть имеет еще одну главную часть. Но мы обсудим это подробно в семинаре. Ну и вот мы хотим здесь проверить, что они действительно, эти штуки, сами W, они не голоморфны, они имеют полюса в точке P, но только с нечетной главной частью. Ну и легко видеть, вот мы, глядя на нашу формулу, видим, что полюса могут возникать только из Q и из D. Больше они из явной формулы, их там нигде больше нет. И это конечная сумма. Поэтому, если у вас есть конечная сумма каких-то кусков, в которых полюса содержатся только вот в этих частях, то, значит, про все выражение вы тоже можете сказать, что вот про каждый кусок мы знаем, что он лежит в си, и конечная сумма, она тоже лежит в си. То есть имеет нечетную главную часть, поскольку это конечная сумма.
А если бесконечная главная
часть? Ну, там могут быть возникнуть какой-то не рано, а когда у вас там бесконечное количество отрицательных степеней. Ну, в общем, какие сложности могут возникать, а с конечными суммой точно не может. А почему конечная сумма, это мы в прошлый раз судили. Вопросы на этом этапе? Мы доказали, естественно, 1/3 в каком смысле логической рекурсии, а именно линейную петлевую уравнение. Ну, это 1/3, это немножко сильно сказано. Не по сложности, а по формальному числу. Остальные вещи сложнее. Но есть ли вопросы про линейную петлевую уравнение? Так, ну хорошо. Okay, so if there are no questions regarding this proof of the linear loop equation, so here we conclude. Let me write it over here. Theorem. L is satisfied. This here I'm a little bit not completely careful because I want, in order to say all that, I want, remember that psi it contains meromorphic functions, the space psi. So we need, in order to say everything like that, we need to say that our W's are meromorphic functions. But they are finite sums of psi primes and y prime. So if you require that y prime extends to a meromorphic function and psi prime again extends to a meromorphic function, then everything is okay. So we need to put some additional requirements that y and psi extend to meromorphic functions on our series. Otherwise, it won't work. Because we need W's to be meromorphic functions, but as finite sums, they become meromorphic functions under this. So if y prime and psi prime of y times z extend to homomorphic functions on sigma. Then all equations are satisfied. Okay. Now regarding the quadratic equations. So with quadratic equations, again, we will want to see that this expression, which we have down below, omega curly 2, that it belongs to the space side. So what we actually want is to obtain a formula for omega curly, the same as for omega, a similar formula for omega curly as we have for omega, for the, sorry, not omega w, curly w, the same as for the regular w's. And in fact, it is possible. So the claim is that, for this curly w, we can write again an explicit formula.
Можно вопрос?
Да.
Когда мы записали топологический рекурсию в формате петлевых уравнений,
Да.
мы там где должны запрещать 0,2 или нет?
Кого мы запрещать?
Ну, говорит, что они для 0,2 не выполнены.
Ну, на самом деле, для линейных петлевых уравнений они для всех выполнены. Там не нужно отдельно говорить. И линейные, квадратичные, они все, они выполнены для всех. Для 0,1, для 0,2. В формате петлевых уравнений нам не нужно отдельно 0,1, 0,2 рассматривать. Они... Единственное, что да, я опять-таки немножко обманул, потому что, как вот здесь было написано, W... Вот здесь вот W это только для WGN, вот эта вот формула, она только для n больше равно 2 и не считая случая 0,2. Такая формула. А для n равно 1 и отдельно 0,2 надо проверять отдельно. Для 0,2 надо просто проверить непосредственно, потому что 0,2 в нашем случае у нас кривая равна 0, она просто dz1, dz2, dz1, dz2 в квадрате, и для чего просто проверяется непосредственно. Сразу верно, оказывается. А для n равно 1, на самом деле, мы имеем аналогичную явную формулу, просто она будет иметь дополнительный член еще. Тут не будет вот этого всего, потому что никаких эгр нет дальше. Вот к этому оператору 1 будет оператору 1 применен к единице, но еще будет один дополнительный член, который мы подробно не разбирали, но мы сейчас не успеем подробно про это говорить, но там он тоже удовлетворяет всем этим свойствам. Для n равно 1 просто надо отдельно смотреть, получающуюся явную формулу, и для нее все тоже увидеть. Еще вопросы? So we want an explicit formula for mobility. And in fact, it's possible to write it. I don't have too much time, so I guess I'll have to skip some parts. But first, the claim is that if you remember, we had the following thing. So Wm with the bullet, the disconnected version of W's, was it could be expressed in terms of in terms of some correlators. It was sum over m1 mn from minus infinity to plus infinity, x1 to the power m1, x1 xn to the power mn, from j n I from 1 to n d sum si j minus I over I h bar and then that. So do you remember these correlators? So we had this formula for W both. So there was some difference between taking the sum between starting from minus infinity and plus infinity, but it was in fact it only changed the 0 to part, right? We discussed it. So we have this formula, and the Wn without bullet, the connected ones, they could be obtained from these guys by applying the inclusion and exclusion formulas. Right? Now we want to define a curly and bullet of U. So we'll introduce some formal parameter U and consider the following correlator. But here I will use this. I can use notation sum from m to minus infinity to plus infinity x to the power m jm. I will denote by j of x. Okay. So this is the product of j of x1 and so on. Right? So now let me introduce the following notation. So what is the difference between this curly W and the ordinary W? The difference basically is in the fact that we inserted here the operator E0. So what was this operator? In fact, we discussed it when we discussed these operators. So E0, if you remember, we had Jm was sum over k half integer case of E k minus m k, while E0 of U is sum over half integer case exp of uk ekk. We use this operator E. We also have this not only 0, but we also have em. Em of u was sum over k exp of u k minus m over 2 e k minus m k. So and also we can define E of u is E of ux by taking the sum over m x to the power m em. These operators curly E, we used them when we studied, remember we had this J bold, and we expressed them in terms of those operators E when we obtained the formula which we used in order to obtain our explicit formula. So now look back here in the definition of curly W. So the thing is that we have plugged here E of HU. Okay? That's the main difference there. And the claim is that or in fact theorem is that if you take W
So the very informal, while Petr Grigorovich is writing the statement, the very informal meaning of what is now going on is for ordinary, so for like ordinary WGNs, WNs or WGNs, we have this closed formula through U operators, using U operators, and now you should, to obtain the closed formula for curly W's, you should take instead of one of this U, instead of U1, say U tilde, which is like will appear.
I haven't yet started.
Yeah. I mean,
first I want to say that the claim is that if we define curly W bullet by plugging E0 here, and then from this we, using the same inclusion-exclusion procedure, we come to the connected counterparts. So we consider W without bullet in a very similar way as how WM is related to WM without bullet. In the same way, we obtain curly W without bullet. And the claim is that if you take the coefficient in front of U squared in the curly W, then this is precisely our curly W2, the expression which we need for the QE, which we need for QE. The guy needed for QLE. Or more precisely, GM. Where taking G is just again taking the respective coefficient in front of us. This is some power of H1. So this is one part, that if you introduce this plug, this curly E there, then taking the coefficient in front of U squared will produce you precisely what you want in this QE expression. This is one part, and the second part, so how much time do I have? Not too much. And the second part is, so I guess maybe on the seminar we will try to look at this. Problem 4. So in the seminar we will try to address this, how to see that indeed this taking coefficient in front of U squared gives you what you want. And another theorem is that this curly W admits an explicit formula of the sort which we had for the order W. So namely, this is what, yes, another theorem is that for n greater than 2, Gn not equal to 0, 2. For n equals 1, again, there is a little modification, which for brevity I will not write right now, but you have that curly Wgn is again h to g minus 2 plus n, u n and so on, u2, and then instead of u1 you get u tilde 1. Gamma product of WKL again VK VL. So basically precisely the same formula instead, except that which we had for ordinary W's, except that one of the operators u for the first variable, because for the first variable we plug this e. Here we have this x1 where e and everything else was the same. So this u is different. So what is this u1 tilde? u1 tilde, let me write it down. So u1 tilde is again, it's quite similar but a little bit different. jr from 0 to infinity, d1 to the power j. It's actually the same formula, you only need to use different L. So LR of Vy Z1 over Q1, coefficient in front of U1 to the power R. This U1 is not the same as U. Remember that in the definition of curly W, we introduced this parameter U. It is not the same as U1. U1, U2, and so on. It's different. So X of U1 times S of U1 S of U1 H bar Z1 Z1 minus 1 applied to minus n divided by U1 H S U1 H F. So here you see that the formula is precisely the same for U. The only difference is that instead of L, you get L tilde. And now let me write what is this L tilde. L tilde R is coefficient, coefficient in front of V to the power J. Here I don't want it. So L tilde R is it's the same, so you get d y plus, what is it precisely? One moment. dy plus v psi prime to the power r applied to x of v s ph bar dy divided by s of h bar dy minus 1 psi of y. And here you only need to multiply this guy by US of VUH bar x plus U1. So the only difference is that LR gets additional factor then, depending on US of VUH bar x plus UY. Because I don't have too much time, I will just say the logic. I will not follow through this in detail, but the logic is the same as the logic of the proof we had for the formula for W ordinary, not for the curly W. The only difference is that you need to consider you'll need to consider J tilde. Do you remember what was this J tilde bold? So J bold was D inverse JMD, right? And J tilde is the same, but you also plug there your curly E. So basically J tilde is this curly E D inverse curly E inverse J curly E D. And then for this J tilde, you can, in a very similar way, obtain similar formulas to this J bold ordinary, and then go through with all your logic over there. Just reproduce all the considerations we made for ordinary W for this curly W. Now let's see, suppose we've managed to prove these two theorems. What does it say regarding the quadratic loop equation?
So maybe let's say that the main maybe technical difficulty in this logic, in this whole proof, is to prove the previous theorem. Yes, that the not the last one, but this theorem that.
For if you restrict it to the just R equal to 2 case, it's not. It's a little bit easier.
Mm.
I think.
Yes.
Yeah. So this second theorem, the logic is precisely the same. You just in place of just curly D, you get D times E0, and then do the same steps, and after that you arrive at this formula where the only difference in this LR. Now let's see what happens with the QLE. We need to prove that WR belongs to the same space side. But looking at this explicit formula again, where can poles arise from? The formula is basically the same. Again, they can arise only from D and Q. The poles can only arise from D and Q. And again, you can see here that this is a finite, when you consider a finite power of U, this will be a finite combination of the functions of the same form, of the functions of the form d to the power j q inverse f, where f is regular. And again, it's a finite combination of these guys. And from there, we can see that coefficient in front of some power of u particular U square will belong to the space psi. And this will give us the quadratic equations, assuming that we also have this the first theorem. Is the logic clear? So I have to skip some parts. Some of these we will do in the seminar, but otherwise, yeah. Any questions at this point? Есть вопросы? Ну хорошо,